Today we will study about the preparations of haloarenes. Haloarenes means arenes, aromatic compound which is connected to the halogen atom, or we can say halogen which is attached to the aromatic compound. So that is the haloarenes. Now we will study today the preparation of haloarenes. First method, by direct halogenation of benzene. This is our benzene is react with halogen in presence of Fe at a dark condition. One of the halogen is substituted in place of one of the hydrogen in benzene. So here we are getting haloarenes plus HX. X can be taken here Cl and Br or Br. Now this is next reaction. Benzene reacts with iodine, but this reaction is carried out in presence of oxidizing agent, that is HiO3 or HNO3. So here again, according to previous reaction, we will get the iodobenzene plus Hi. Here if the reaction is carried out in presence of any out of this one reagent, then whatever the Hi we are getting here, it will not oxidize back to H2, I2. So reaction is going in forward direction only. Now next reaction is toluene. Toluene react with Br2 in presence of Fe in dark condition. One of the Br is replaced this hydrogen. So here we are getting orthobromotoluene or parabromotoluene. And HBr. Now above electrophilic substitution with iodine is reversible. This reaction is reversible by use of oxidizing agent HiO3 or HNO3 stops oxidation of Hi to H2. Iodide product is formed, and fluoro compound is not prepared by this method because F2 being a highly reactive. This method of preparation of haloarene is Sandmeyer's reaction. Now in this reaction, when aryl halide can be obtained most satisfactory by the decomposition of aryl diazonium salt. This is our aryl diazonium salt in the presence of copper chloride, copper halide solution dissolved in a corresponding halogen acids. This is our copper halide which is dissolved in corresponding acid. We can use this also or Cu2Cl2 also. Out of these two we can write any one of the reagent we can use any one of the reagent. Now the azo group here is replaced by the halogen atom, then that reaction is called then Sandmeyer's reaction. This is our benzene diazonium chloride. When react with CuCl in presence of HCl or Cu2Cl2, then we are getting here haloarenes, that is if halo is chloride, then we can say it is a chlorobenzene plus N2. Now if we are using CuBr in presence of HBr or Cu2Br2, we will get a bromobenzene. And suppose if we will use CuCN or KCN, then we are getting cyanobenzene because cyanide group is attached to the benzene plus nitrogen. But now see, benzene diazonium chloride which we used for the preparation of haloarenes, this is our component, but we will prepare this also from by using the diazotization reaction by using aniline. Now we'll see, aniline reacts with sodium nitrate. C6H5NH2 means NH2 group if attached to the benzene ring, then the name of that compound is aniline. Aniline reacts with sodium nitrate NaNO2 in presence of HCl at 0 to 5 degrees Celsius. Here we will get N double bond N, benzene attached to the N double bond N and Cl. Okay, so this is the compound benzene diazonium chloride, and rest of the thing will form a byproduct. Now the next reaction is reaction of haloarenes with metals. This reaction is a name reaction, is also called as a Woods fitting reaction. Now we'll see the reaction of aryl halide with alkyl halide and sodium metal in triether to give a substituted aromatic compound. This reaction is known as a Woods fitting reaction. This is the haloarenes because bromine is connected to the aryl, so it is a bromobenzene. This is the aryl halide, this is the alkyl halide, aliphatic alkyl halide. Okay, so this is CH3Br, means aromatic alkyl halide and aliphatic alkyl halide, both are present here, and these two reagents react with sodium in presence of dry ether. So what we will get? C6H5CH3. Okay, so this will substitute it and CH3 will connect there, and all these things will form an addition compound, that is twice NaBr, and in place of Br CH3 will add. So this is our compound toluene, and this reaction is also called as a Woods fitting reaction. Now here two molecules of alkyl halide, aryl halide we took, that is a chlorobenzene here. Chlorobenzene, when only aryl halide take part in the reaction, then the product is biphenyl, and the reaction is known as a fitting reaction. This is the two molecules of aryl halide react with two atoms of sodium in presence of dry ether. So here this benzene ring is connected to itself only. So here we are getting biphenyl plus twice Na, two molecules of Cl. So twice NaCl will be the byproduct. This reaction is a fitting reaction. Now this is the Woods fitting reaction, this is the fitting reaction. What is the difference in both the reactions? Here we are taken here out of two. One is aryl halide and one is aliphatic alkyl halides. Here we are taken both the reagents, both the molecules of aryl halide only. We are not taking any aliphatic alkyl halide. And that's why this reaction is a fitting reaction, this is the Woods fitting reaction. This reaction is electrophilic substitution reactions of haloarenes. Now from this structure it is observed that due to resonance, electron density increases more at ortho and para position than at meta position. From these structures you can observe that, see, here the electron density is very high, it is the ortho position. After the rotation it comes here, that charges come here, so electron density is very high at para position. After the rotation again in the next structure, electron density is increases at again ortho position. Means from this all these resonance structures we can observe that the electron density is very high at only ortho position or para position than that of meta position. Okay, so electrophilic substitution reaction takes place only at ortho and para positions. This is our ortho and this is our para positions. Now see, this is the chlorobenzene, is reacts with chlorine in presence of anhydrous FeCl2. Chlorination reaction is carried out. Here the next chlorine is replaced by this position because this is the ortho and this is a para position. So here we are getting the two product, para dichlorobenzene. One is here already, those we are having the in our reagent reactant, and after that this Cl is replaced this hydrogen by Cl. So here again Cl will attach here in presence in place of hydrogen. So this is the compound para dichlorobenzene and this is the ortho dichlorobenzene. Now same reactant is reacts with HNO3 concentrated in presence of concentrated H2SO4. The reaction is a nitration, and during that reaction NO2 group, that is a nitro group, is attached to ortho position as well as para position. So again here we are getting the two product in which one component is having the nitro components at para position and one component is having the nitro components at ortho position. Now see which one is the major product. In both the reactions the para dichlorobenzene here is a major component and 1-chloro-4-nitrobenzene. This is the major product here because of the symmetrical structure than that of this, and this is the minor product in this reactions. This is the compound chlorobenzene, reacts with concentrated H2SO4. Heat, this reaction is known as sulfonation. Here from H2SO4, SO3H group will attach at para position or as well as ortho position. So see this reaction, see this product. Here Cl is already there and SO3H is attached to para position. In this next compound, here SO3H is connected to the ortho position. So this is the ortho-chlorobenzene sulfonic acid. This is para-chlorobenzene sulfonic acid. And this also is the major product. Now see, chlorobenzene react with CH3Cl. in presence of anhydrous aluminium trichloride, AlCl3. This reaction is known as alkylation, and while reacting these two components, what we are getting, say, this is the chlorine is already attached here in on benzene ring, and one of the hydrogen is replaced by CH3 alkyl group. So CH3 is attached here. So para-chlorotoluene compound is formed. Is like this, ortho-chlorotoluene compound is formed. This is the major product by the rule. And after that, third reaction is chlorobenzene again reacts with CH3COCl, that is acetyl chloride, in presence of anhydrous aluminium trichloride. This reaction is known as acylation reaction. And what is the product we are getting? We'll see. This is the chlorine is already attached to the benzene ring, and one hydrogen is replaced by COCH3 group, and that hydrogen combined with HCl, that is the byproduct. So COCH3 is attached to the ortho para position here. So what is the compound? Parachloroacetophenol. Now here COCH3 is attached to the ortho position. So this is the name of that compound is 2-chloroacetophenol. Now here, whatever the para compounds are there in all these three reactions, these are the major product because of the symmetry of the compounds is very high here. And these two reactions we will going to study under the Friedel-Crafts reaction, because Friedel-Crafts is having two parts. One is alkylation and second one is acylation. So these two reactions will come under the category of Friedel-Crafts reaction. Next one is nucleophilic substitution reactions of haloarenes. Aryl halide are extremely less reactive towards nucleophilic substitution reactions because of the following reasons. First one, resonance effect. In aryl halides, CX bond acquires a partial double bond character due to the resonance. As a result, CX bond cleavage in aryl halide is very difficult than alkyl halides, and therefore they are less reactive towards nucleophilic substitution reaction. All these are the canonical forms of haloarenes, and this one is the resonance hybrid structure of haloarenes. From this you can see that the electron density is very high in para and ortho position, as well as in between C and X double bond character are exist, and because of due to a double bond character it is very difficult to break CX bond, and because of this thing it is very difficult to show it is less reactive to show a nucleophilic substitution reaction than that of alkyl halide, because there is no any double bond in alkyl halide. Second point is that difference in hybridization. Now this is haloarenes. You can see this carbon, the carbon which is combined to the halogen. Here, this carbon undergo sp2 type of hybridization. So we can say that this is the sp2 hybridized carbon atom, because during the formation of benzene ring, all carbon atoms undergo sp2 type of hybridization. And to this sp2 hybridization, whatever the hydrogen is there in benzene ring is replaced by a halogen atom, and there is a formation of haloarenes. But this carbon is originally in the form of sp2 hybridized carbon atom. In case of alkyl halide, if you see this structure here, carbon in alkyl halide, it must undergo sp3 type of hybridization, and because of this, percentage of S character is very high, and that's why it is less reactive towards a nucleophilic substitution reaction in haloarenes. Third point is the instability of phenylcation. This is the third point in why the nucleophilic reaction is less reactive for aryl halide than that of alkyl halide. So third point for that topic is instability in phenylcation here. Now in case of haloarenes, the phenylcation form as a result of self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is ruled out. Now in haloarenes, the phenylcation, whatever the phenylcation, we already saw the resonance structures of different canonical forms of haloarenes. So whatever the phenylcation is formed as a result of self-ionization will not be stabilized. Means it is unstable by resonance, and therefore SN1 mechanism is ruled out, because we already know during SN1 reactions it is a two-step reaction, and first step is that formation of cation, and it must be stabilized, then only the next reaction can be proceed. But here it is first cation, whatever the phenylcation is formed during the resonance, it is unstable, and because of this SN1 mechanism is ruled out. Second one is that backside attack of nucleophile is blocked by a aromatic ring. Whatever the aromatic ring is there in aryl halide is blocked the nucleophile attack from backside, and because of this, because SN2 mechanism is also ruled out, because in SN2 mechanism front side attack and back side attacks, both the process are carried out at one time simultaneously, and this is not possible here, and that's why SN2 is also ruled out, SN1 is also ruled out. Means both the nucleophilic substitution reactions are is very difficult here in haloarenes. But the presence of certain group at certain position of the ring markedly activate the halogen of aryl halide towards substitution reactions. Now see, in haloarenes, suppose any certain groups are present at a certain position of the ring. So under that situation, in presence of certain temperature and catalyst also, the nucleophilic substitution reactions can be possible. Now see, this is the component para-nitrochlorobenzene. Para-nitrochlorobenzene. It reacts with NaOH and H3O plus at presence of 433 Kelvin. This is the temperature which we will apply here for that reacting. So Cl is replaced by OH and NaCl is the byproduct. So there is a formation of that compound. Means the substitution is carried out at this position. Now in second case also, 2,4-dinitrochlorobenzene. This is the 2,4-dinitrochlorobenzene. Here reaction is carried out in presence of aqueous Na2CO3 at 403 Kelvin and H3O plus. Then this Cl is replaced by OH. So there is a formation of 2,4-dinitrophenol. Third reaction is 2,4,6-trinitrochlorobenzene. This is the 2,4,6-trinitrochlorobenzene. It's formed in presence of water. So OH can be entered here in presence of in place of Cl. So there is a substitution reaction can be carried out. 2,4,6-trinitrophenol can be formed.